migrating into those structures. And it might be that though the reason that we don't see obvious flat spots in offshore Lebanon in the deeper parts of the early Miocene play is just because it's not gas, it's oil. It's an oil play. And then the question becomes, well, just how big could this oil play be? I would say before moving off this slide, although you're quite capable of reading it as I'm wittering away here, but moving off this slide, evidence for there being a working oil system is present in Lebanon. And it comes from a series of oil seeps, natural oil seeps that you can see on optical seep data. You can also see it on SAR data. And in general, it runs parallel to the coast, quite close to the coast. So this has led the sort of thought process to be that quite near to the coast, there's a working oil system. And so people have looked at Jurassic type of source rock and Jurassic systems working quite close to the coast. But it's not quite how this basin works, because if we take this as being the Oligocene in here, and we start cooking it and generating oil, that oil comes up and then it starts to migrate beneath the Messinian salt layer, which in this area is more or less planar. And so typically the oil will then migrate along the base of the salt and pop out quite close to the coast. So the fact that you see oil close to the coast just means that there's a working oil system in this basin, not that it's only close to the coast you're going to find oil. It's quite an important distinction. So what other evidence have we got that there may be an oil system here? So this is the familiar slide that we had before of the discoveries, the dry gas discoveries. Leviathan itself was deepened and the operator started to report the fact they recovered liquids. They pretty soon stopped doing that because I think everyone got the idea it might be an oil basin and get very excited and competitive about offshore Israel. But they did report initially the thermogenic liquids in the deep Leviathan structure. And then they've drilled another structure called Karish. And Karish is located much closer to the border with Lebanon. And at first it looked like just another rather boring gas discovery, would just be tied into the other discoveries in the fullness of time. But then, and I have to say it's apocryphally, I don't know this for sure, but then it was reported that Karish was slightly different because it too had recovered liquids. It was a gas condensate. So where does this gas condensate come from? Well, it comes out of the northern Levant basin and it just migrates up dip into the Karish structure. Karish structures itself is quite interesting because this is the Karish well drilled right here, and here's a couple of lines that are close to it. This is the early Miocene section, and it looks like it pinches out as you come up dip onto this structural feature here. So Karish, I think, has got up dip closure, and it tells you where that early Miocene sand has an up dip termination. So that allows us to, looking at the whole basin, mapping this up-dip termination of the early Miocene sands, that allows us to make this map. And this map is our view of where the early Miocene sand onlaps. Now, it may not be exactly right, because in this area, our colleagues, PGS, have 3D seismic data, and they could probably nail down that pinch out better than I can do it on 2D data. But in principle, the early Miocene sand is filling the deeper part of the northern Levant basin, and it's not necessarily gas prone. It could be an oil play in that basin. So here's a bit of a story about a potential oil play that might be working in the northern Levant basin. So how does this affect Karish or Zor? And conversely, how does Zor affect this story? So from what we understand at the moment, the Zor feature here is an early Miocene reef. So it's grown at the same time as the sands, the turbidite sands that form the reservoir in Tamar and form the reservoir in the northern Levant basin coming into the basin. It's an early Miocene reef, and we understand that the gas is a very dry gas. Now, nobody's said that it's a biogenic gas, but the odds are it's the same biogenic gases you get in Tamar and so forth. So it says something about the deposition rate and the substance rate and the geotherm around the Eratosthenes seamount. So it's a gas story, and it doesn't corroborate an oil story, and I want to be very clear about that. When the discovery was made, of course, because we've got seismic data, well, it's a little bit of an advert, but I mean, Spectrum itself has got 3 million kilometres of 2D data all over the world. So when anything happens, we go and have a scurry through the data and see what we can see for that discovery. And in this area, we have quite a lot of data, predominantly to the north of Zohr. So the first thing we wanted to do is see if we could see Zohr, and we can see Zohr now, although I have to confess I couldn't see it beforehand, and it helps when it's coloured in. But we can see it now, and then of course having got our eye in, so this fuzzy sort of imaging is not just poor seismic imaging; it's actually the reef part. In the middle, you get a bit more coherence, so that's probably a lagoonal facies, and then you get some more fuzzy reflectivity. So, having got your eye in and suggesting, well, that's probably not just seismic imaging, it might be something else. We went looking around for other features like this. So, this feature, Zohr features 100 square kilometres. So we went looking around. It didn't take us very long to spot this feature, which has got fuzzy reflectivity on either side and then rather coherent reflectivity in the middle. So when I put that on it, you get a sort of Zohr lookalike creature. And this one is not an itty-bitty, almost can't see it, 100 square kilometres. This is a 500 square kilometre carbonate reef, and it's just sitting again on the Eratosthenes seamount, on the edges of it, and covered by Messinian salt. And these are probably the key play elements that we need to think about as we go look for these features. Here's another example, just a little bit further along. Again, I think we've always seen this big knobble sticking there, but we never actually knew what it was. So now I think we've got an idea that these are early Miocene carbonate buildups. And presumably they all have some prospectivity rather similar to Zohr. So if those were predominantly north-south type lines, this is an east to west or west to east line going over the Eratosthenes seamount, which is this guy in here. And this is the northern Levant basin, so you can see Leviathan and Aphrodite with the early Miocene reservoirs in here, and then these big carbonate buildups, which actually sit on both sides of the Eratosthenes seamount. The Eratosthenes seamount itself, if you can just bear me a slight digression, it's really, really cool because even though now it's in like 1,500 metres of water, just shy of 1,500 metres of water, at the time of the Messinian, they were depositing paleosols there. So the Eratosthenes seamount was exposed at the time of the Messinian salinity crisis. So it strikes me you do this two ways. One is that you either pull all the water out of the Mediterranean, which I like, but not everybody likes, so that you completely desiccate the Mediterranean. And the other way to do it is to very rapidly, since over the last 6 million years, you very rapidly subside that whole seamount, and probably due to the fact that it's being pushed under Cyprus at some point, and that sort of tectonic forcing of this subsidence. But the interesting thing is that this exposure may relate to the carbonate build-ups that are all around the Eratosthenes seamount, and presumably they were exposed, maybe they developed a karstic porosity at that time, and maybe that's why these carbonate build-ups are going to work. And I'm sure in the audience today, we've all drilled carbonate build-ups which didn't work for one reason. Well, okay, I've done it, but I don't know if everybody's done it. And this may be one of the things that will make this play repeatable, and I think that's going to be important, as was mentioned by Stephen. It's just one well in one carbonate bank. We have to make this repeatable to add the significant reserves. The Eratosthenes seamount, which is located here, is supposed to sit on attenuated continental crust, and that the oceanic crust is basically to the west and generates the Herodotus basin and so forth. That's the conventional model. I don't know if we actually really know any of that. I don't know if we actually know what the Eratosthenes seamount is made of. It may be just a bit of folded oceanic crust for all I know. All I know is it's sticking up in the early Miocene, and we were growing reefs around it, and that's probably all we need to know at this stage. So if we take another line here that runs around the seamount, you can see numerous of the zorettes just sort of growing around there. So there's huge potential in that area to the north. My understanding is that there are more of these carbonate build-ups offshore Egypt, not all of them in the E&I acreage as well. So I think that this part of the world has huge potential that will roll on from Zor because of this repeatability. So very lastly, then I'm just going to very briefly talk about structures. So I'm going to migrate back to the east and fall into the northern Levant basin, because from the basis of this 2D line, you see all these faults in here, the basis of the 2D line, it would seem to justify the model that the northern Levant basin is just shattered by faults, and that it's hopeless finding anything in the northern Levant basin because there's so many faults that you need lots of wells to develop it, it's deep water, yada yada, you can't make it commercial. Just not true. So, when we compare this map here, this is a map of some of the structures we were just looking at. The thing is, that was a really, really long line that has been squashed up, so no wonder it looks busy. These structures here are of the same size as Tamar, so here's Tamar, and they're the same size, and to be honest, they're less faulted than Tamar is. And if you look at Leviathan, you know, if I had £1 for every fault on Leviathan, I'd quite a few pounds. Because here it is here. I mean, it's not shattered, but it's just lots and lots of faults. Now, Leviathan is saved because it's a ton of sand, so across these faults, it's unlikely you're going to get fault sealing. But this is a kilometre of sand too in the northern Levant basin. So these are going to be very simple structures, very easy to develop, and they won't need too many wells. And my guess is that they will be developed extremely quickly in the E&I aspiration, or in the noble, yeah, we've done that, model, where they just do subsea tiebacks and tie these things straight back to the shore. Of course, it won't be as easy as that if it really is oil, because these will be billion-barrel fields that you'll have to develop properly, and it will take more time, but probably more value. So a couple of examples of the structures in the northern Levant basin. This is a surface within the Miocene unit, and it shows one of the wonderful things about this basin, and that is that the faults that are virtually east-west faults here are all more or less parallel to each other. So you've got these east-west faults across here, and these are crossed by large fold structures which push through the structure itself. Now, the formation of these piano key faults, these vertical faults, there's still a bit of debate on it, but the model I particularly like is the one that's developed from field examples in the canyonlands of Utah. Can we negotiate on that? Right. Yeah, okay. No more than 5 minutes. Probably. Yeah, okay. Right. Counting now. Okay. Hold on to your hats then, as we go into the explanation of these faults. Because it's so easy peasy. What you have is a detachment surface below this sequence of fairly brittle material, and these faults just root straight into that detachment surface. In this case, in Utah, it's salt. So you know it's mobile, you know it's a detachment surface. You see exactly the same faults in the northern Levant basin, but there's no salt underneath it. There's something else. There's the thick Oligocene section. Now, if that was a thick Oligocene shale and it was just hard, brittle shale, these faults would not detach into that shale. They would go straight through it into the Cretaceous, but they don't. They stop in the Oligocene shale. The reason they do that is that the Oligocene is the source rock, and it's generating hydrocarbons, and it's actually viscous, so it's deforming as if it was a mobile unit. And what this creates is a kilometre of sand sitting over a Oligocene source rock, big structures, big individual structures. So each of these structures here is Well, the equivalent of about a billion barrel field, if you want to put it in that order of magnitude, or 7 to 9 TCF of gas if it turns out to be gas. But what's really cool about the middle of the Northern Levant Basin is that these structures all connect up, and they connect up into this monstrous ridge in the middle of the basin. And so this potentially gives you the repeatability thing, in that you can drill Cronus structure here, and it's got to significantly reduce the risk on all of these features because they're all within the same closure. So this is what will happen when Northern Levant is actually explored, the offshore Lebanon, is that we'll have one successful well, which can be developed really quickly, but we'll just have that repeatability. Sounds a bit like an explorer getting ahead of himself, but this is exactly what's happened just to the south offshore Israel, where Noble just drilled well after well after well and then found 50 TCF. So in the actual detail of the structures, we've mapped them at all sorts of levels of detail. The level of complexity is no more complex than Tamar, so it won't be any less developable than Tamar. So we go to the Northern Levant, ask 3 questions again. Is it just a biogenic gas play in the Northern Levant Basin? No. It's probably an oil play as well. Does offshore Israel have the thickest, best quality reservoirs in the Levant Basin? No. Go to the Northern Levant Basin, you'll find them 3 or 4 times as thick. And are the best structures in South Lebanon? No. The simplest structures are in Northern Levant Basin. So then, last slide. Yay! There you go. As Andy Warhol has showed, you can rush art. So, last slide. This is what we found to date. Something like 100 TCF in the Nile Delta, whether it be in the Pliocene, in the Miocene, and these super deep wells that are being drilled, or the Abamadi. So something like 100 TCF there, and something like 50 TCF offshore Israel. Following Zohr, there's got to be 50 TCF in the Zohr analogues that wrap around the Eratosthenes seamount. And on our evaluation in Northern Levant Basin, there's probably another 50 TCF at all. And if you just go by closology alone, you can see that there's some potential truth in this. And this shows you what will keep coming out of the Eastern Mediterranean, and I would heartily encourage you all to explore it if you can. Thank you.
Thank you.